All right, so today we're going to be talking about chapter 13, which is looking at freshwater streams, lakes, and groundwater. Now, when we start looking at freshwater, we are saying that this is water that has less than 500 parts per million in dissolved salts. And so if we start looking at um, ocean water, we're talking about 3.5 parts per million. And so this fresh water is pretty rare stuff. It's only about 2.5% of the world's water is currently fresh water. That it includes ice caps. And so we can look at this little breakdown of the vast majority of the water is in fact saline ocean water. Then we have, of that freshwater portion, we have the majority of that is trapped in glaciers. We have about 30% of that fresh water in groundwater. Some of that we can obtain, some of it is too deep for us to get. And then we have the rest of this in things like freshwater lakes and springs. And so we can see we're getting smaller and smaller and smaller fractions of materials here. Um, so let's get started on this little fraction of the water, which does a really number on the surface of the landscape. So first of all, we start looking at the water cycle. It's driven by uh, solar power. It's water is rising up through evaporation and then falling as rain and or sleet or snow. And so when we start looking at water moving over the landscape. This water moving over the landscape is called runoff. And water flows under the force of gravity, moves down slope, but it can channel. And if it starts to channel, it'll start to create little tributaries, which are going to cause this water to cut deeper and deeper and deeper. And so we're going to end up with eventually streams developing from the sheet wash. So excess water is going to be coming from rain and snow and melting ice and from springs. We'll talk a little bit about springs in a couple of chapters. On flat ground, water accumulates in puddles or swamps. And after a glacier retreats, the water has no real defined place to go. And so we actually call that deranged drainage, where that water just doesn't know exactly where it's going to go. But overall, the water is going to follow the path of least resistance and move downhill. And so when we start looking at this water, you can start to see a couple of terms where we start looking at water, where water is coming from. These are typically called the headwaters. Water flows out eventually at the bottom of a stream. It goes into a mouth. I do want to talk about a couple of things here. First off, looking at this slide, we can see that there is the water table. This is where all the cracks and crevices are filled up with water, and that water is always moving. Water never stands still for long. It's always going to be moving, whether it goes into the ground and it moves as groundwater, whether it's runoff or it goes in a river. It's always going to be moving. And in order to track the water, what we want to do is figure out looking at some things called drainage networks. This can tell us a little bit about the landscape and where is the water going. So the first thing that we need to talk about when we look at these networks, drainage networks, is we need to determine what is the drainage basin. Now, in a chapter, when we start looking at topographic maps, these are maps that show elevation, and we can look at um, all of the area that is contributing to a river flow is defined as the drainage basin. And so we can think of it as a wash basin, where any rain that would fall in a wash basin would end up in the bottom of that basin. And so that's why it's called drainage basin. The boundary, the edge of that basin, is called a divide, a drainage divide. And so when we start looking at these different drainage networks, there's a number of different ones. Your book looks at a handful of one. The first one is the most common, and it's called a dendritic pattern. Now, dendritic, as you already are pretty sure aware, dendra means tree, and so this is a tree-like pattern. And so we have, you may have heard the description of branches talking about tributaries of these small rivers. And so if weathering is the dominant feature in this environment, then rivers are going to have this dendritic pattern where the further and further downstream, the rivers are going to be getting larger and larger as these small little branches are forming together to form the main trunk of the dendritic pattern. If we have rocks that are um, heavily folded, or we have some rocks that are more resistant to weathering, then we can end up with something called a trellis pattern. It looks kind of like a row of grapes. This tells us that these rocks have been heavily folded, and we know that from previous chapters, this is going to be associated with um, mountain building. So just looking at the river breakdown or these trellis pattern, we know that we're in some areas that were at one time in the past where the rocks are no longer flat, but have been buckled up. If we have a volcano, that point in the middle of the volcano is actually going to be the high point with the drainage divide for, or the drainage divide for a number of different basins. And so each river would have its own drainage divide. And so that point right in the middle, or of this radius of look like spokes of a wheel, um, would be another example of another drainage basin. Again, if you're in that area, you may want to buy volcano insurance if you have an area that is prone to volcanoes. Um, you can have parallel streams. Again, kind of like uh, sorry about that. You can have parallel streams that are very similar to trellis. Again, rivers in parallel there indicate that the rocks have been buckled in a slightly different fashion. If you have rectangular fashions, these are where rivers are going to follow pre-existing cracks or joints or faults. And so if you have these 90-degree bends in a rock, you might want to buy earthquake insurance. So looking at these drainage basins, we can learn a lot about the environment without actually looking at the rocks. So the first question of the end of the chapter quiz is which of these is not a draining system? We already talked about all of these except for brachipod. There's your hint. When we start looking at these different patterns again, we have identified all of those. So here's an example of the drainage divide. Now we can look at a topographic map and find where rivers are flowing into one direction and rivers are flowing in another direction. You'll recall from a topographic map that contour lines make these V shapes that kind of go point uphill. And so we can see these rivers are getting smaller and smaller. And then we'd have a ridge in between, or an area that would separate water that is sloping to this river from water sloping into stream B. And so that line in between would be a drainage divide. And we have probably the most famous divide in the United States is the Continental Divide. It's called the Continental Divide. It's called the Continental Divide because it divides water flowing from the Atlantic Ocean, whether it be the Gulf of Mexico or the direct Atlantic proper, or the Pacific Ocean. And so this is that continental divide. There's lines or there's signs for it all across the western part of the United States whenever you cross that divide. We have the Appalachian Mountains, by and large, as a divide that separates water flowing from the Atlantic Ocean into the Gulf of Mexico. We have up in Canada, most of this area is going to flow into the Hudson Bay and then out into the Atlantic Ocean. And so there's kind of an interesting point here. This is in Glacier National Point. It's called Triple Divide Peak for obvious reasons here, where if you poured water on this and it didn't evaporate, part of it would go into the Atlantic, part of it would go into the Arctic, part of it would go into the Gulf of Mexico. And so that's a unique boundary. This is another unique location. It's called the Great Basin. It's an area that doesn't get a whole lot of rain. If it got more rain, it would fill up. But the only thing that happens is water flows into that region, and then the only way to get out of that area is through evaporation. If we had more rain, again, it would fill up, and then the water would eventually flow out one of the sides. But that's not the case. So when we start looking at rivers, one of the things that we want to know is how much water is flowing out of a river. And so the measurement that we're using to calculate how much water is passing through a river is called the discharge. Now, discharge is always a volume per unit of time. And so here in the United States, we usually talk about cubic feet per second, or CFS. And so when we start looking at this, we want to know there's some nuances to this, but what we really want is the discharge is the average area times the average velocity. Now you'll note that if we were just looking at this river, we have faster parts of the river and slower parts of the river. And so as a field study, what we want to do is look at the dynamics of this river. And there's been enough studies to know that about 40% of the way down at any given location is about the average speed. The water in the middle of this stream, is the technical name is the Thalweg, where the fast part of the river is going. Now, why is it so much slower on the edges? Because there's things sticking up. These are rocks, and any particulates in the anything on the edges of the rivers or the banks of these rivers, the stream bed, is going to cause an impedance, and it's going to slow this material down. So we can actually collect the amount of water or the discharge at any given river at just about any time. There's a number of monitors that are actually collecting this information as we speak. And so what we have here is a little intake that is measuring how fast this water is moving and how much water is in this river valley. We've already mapped out this river valley, so we can calculate that discharge. Now, if we wanted to, we could actually draw in, I'm going to make we figured out the average area of this supposed to be rectangle. If this was 5 feet deep and 10 feet wide, the cross-sectional area would be 50, sorry for my bad writing here, 50 feet squared. And if this water was moving at 2 feet per second, every second it was moving 2 feet, then the average discharge of this would be 2 feet per second. Would be 100 cubic feet per second. And so here's every one of these dots here represents a rain gauge, a stream flow gauge. And if you clicked on any one of these, we could actually see how much water is flowing. Now, as I'm recording this, we had some rain in the last week, and you can see when we have the rain, the water jumps up. What we have here is, this is the Big River in Desloge, and about 7 years ago, they redid the access road parallel 67, and they put in a new rain gauge. They had the old data, but since they redid it, they only are collecting data for the last 7 years. And so the 7-year average, we can see prior to the rainfall events that we've had this week, it's been pretty dry around here in this fall. And so as a result, the water is much lower. And so again, you can see that the discharge is in cubic feet per second. Now, one of the other things I do want to note is that on this discharge calculation or the scale, it's an exponential scale. It increases at an increasing rate. If we wanted to actually see what's the height of the water, we can do that too. And again, this is just measured directly by those rain gauges. And it's usually, we'll send this information through radio waves and a little solar panel. So you can set these up just about anywhere and collect this data to the USGS and click on that stream flow webpage. And so if you type in USGS stream flow, it should get you into this right location. So when we start looking at rivers, the greater the discharge, or the greater the velocity, the greater the discharge. If the river were to double in speed, you get more water out. The other thing that you can do is increase the area. And so if you have a river that overflows its banks, it's going to really increase the cross-sectional area. Now, this comes into play a number of different ways. The first one is when we start looking at a flooding event, because we go from a small area in these rivers to these really big areas. And so what's going to happen when the river overflows its banks, it's going to substantially slow down. because if the discharge is the same, if we increase the area, we're going to decrease the velocity. The same works, the converse works as well. If we cause this water to be restricted, the water is going to speed up. And think about if you had to go and wash your car, putting your thumb over a garden hose with the average discharge is pretty uniform, but putting your thumb over the hose is going to cause the water to speed up. And when the water has a smaller cross-sectional area, what's going to happen is that water is going to be moving a lot faster. And we can mathematically calculate what that would be if we knew those actual precise measurements. And so as a result of this, water speeding up and slowing down, you can introduce something called turbulence. When water can't flow in a straight path, it's going to have to get slowed in some areas and sped up in others. And so this is going to create something called turbulence. And so when we start looking at water, rivers can be classified into either permanent streams or ephemeral streams. Permanent streams are when we have water flowing throughout the entire year. Water is fed, even we can look at the Mississippi River, even though that we had a drought in this area this fall, we still had a lot of water in the Mississippi River because, as it turns out, that this water is actually flowing from the groundwater into this river. The amount of potentiometric water in the groundwater in this area is actually going to push this water in and force that water into the permanent stream. And so anytime that you have a river that doesn't dry out, it's going to be one of these permanent streams. We can contrast this with these ephemeral streams, which are only around during part of the year. Maybe after a heavy rainfall, you have some water in these areas, or in the spring when you have more rainfall, it'll be there. But then in the summertime, what can happen is the water table can lower and these rivers will actually go and dry out. In places like Arizona, we call these things washes or dorados. And as it turns out, the water will go into these regions, and sometimes these ephemeral streams are called the losing streams because the water would go from the river into the ground. And so, yeah, these are ephemeral streams. So what an ephemeral stream is a stream that only is formed during part of the year. So sometimes these are also called intermittent streams because it depends on the time of year. And on a topographic map, we can see that these intermittent streams are these little dashed lines followed by solid lines. And so if we take a look further downstream, north on this map here, the water, we have a permanent stream. Now, as rivers are moving down, they're always going to be they're going to break down these little bits of water. Water is a very effective agent at removing materials. And so we call removal of materials eroding. Then we're going to be, rivers are also really good at transporting and then also sorting and depositing sediments. So as the rivers are eroding, they're going to be carrying away little bits of rock in them. And so just like a sandpaper is really effective at sanding down surfaces, the water carrying little bits of sand are going to be scouring these particles. And so what can happen is these little bits of rock can break off and then they can actually be very effective at scouring. Water is the universal solvent. And so if you have minerals that are easily dissolved in water, we can get dissolution. And then finally, abrasion. And so as a result, you can create these potholes. This person is, you can see this pothole here from your textbook. And this looks like a river canyon that's been carved out. It looks like Antelope Canyon in Arizona. If I just had to guess where that image is from. But we can also see some local examples. Here's a classic example of Johnson shut-ins in mineral area just outside of the Arcadia Valley, where the water is literally shut into these igneous rocks because igneous rocks are more resistant to weathering than sedimentary rocks. And so the water is shut in. If it's shut in, it's going to speed up. And if this water has little bits of sediment in them. This water can abrade to create these potholes, which on a summer day after a good hike, I really enjoy going to these shut-ins and kind of getting this water to have this little waterfall on my back after a good day of carrying my backpack around. Um, but again, so we have some local examples of these rivers. Um, so as rivers are moving sediments downstream, we can look at a couple of different ways in which rivers carry materials down. The first one is the fact that I already mentioned water is the universal solvent. So you're not going to see this load, um, but it's called the dissolve load. It's in the water and it's constantly carrying salts down to the Gulf of Mexico around here. Remember that Great Basin I was just talking about a couple of slides ago? Water doesn't end up in the Pacific Ocean or the Atlantic Ocean. It goes into that same area and then the water evaporates. And so the dissolved load is left behind. And so when you start looking at the southwest part of the United States, it's not uncommon to get salt flats. The Great Salt Lake is an example of a river that is, or a lake that is a salty lake because of this dissolved load. If you've ever seen the Mississippi River, you'll realize it's muddy. Little bits of silts and clays are so small that the slightest bit of agitation of this water can keep this sediment aloft. And so we call this suspended load. When we start looking at the competence of the river, one of the things that we're going to be looking at, what's the biggest particles that can be transported down? And so these are going to be moving along the bottom of the river, and these are this would be called the bed load. You may have experienced this if you've ever gone floating around here. A lot of times, if you just stand in the river, this bed load, you can be an impedance to this bed load, and you can actually have piles of gravel building up on the upstream side of you just standing around in the creek. So then we also can look at the total of the suspended load plus the dissolved load plus the bed load. All of that material is the capacity of the river. And so that's how much sediment is being transported down. So what's the maximum size? It's the competence. So when we start looking at a river, this is a fairly common process to see. This is a hypothetical river here with the river valley here. Next to each river, we have these little high regions, and these are natural levees. We'll talk a little bit about these natural levees being formed as the rivers occurring during a flood. One of the other things that occur is these big, broad, flat regions next to a river known as a floodplain. If we look at this material in a slightly different angle here, we can end up with these piles of material pointing out into the river, and these are called point bars. And sometimes if they're made of gravel, we'll call them a gravel bar. If they're made of sand, we'll call them a sand bar. We call all of this material collectively alluvial material or alluvium, which are river deposited materials, as opposed to something like till, which would be glacier deposited materials, or aeolian for wind deposited materials. But this is a chapter on rivers, so let's stick to alluvium. Now, when we start looking at rivers, one of the things that we're going to be looking at is the gradient. Now, I'm sure you've already familiar with the gradient of a line is x1 minus what? y1 minus y2 over x1 over x1 minus y2 over y1. In our class, we're going to be looking at the rise over the run, the change in elevation divided by the run of the river. And so it's not always going to be in a straight line. We could follow the course of the river, and it's going to be a lot more miles because these rivers are not nice and straight. But we can actually look at the gradient as the rise over the run, the change in elevation divided by the change of length. And so we can look at places like the Black River, which has a gradient near the headwaters, near the upper regions, of somewhere around 7-8 feet per mile. Whereas opposed to further down south of Lake Wappapello, the the gradients is something like 2 feet per mile. Now, when I was doing my grad work, I looked at some of the big rivers like the Mississippi River and the Ohio River. I was in Illinois. And the gradient of these rivers are something like a couple of inches per mile. So it's relatively flat. Um, and so these rivers are constantly moving down for long periods of time. And eventually these rivers are going to wash into the ocean. And so the ocean is the lowest elevation in which a river can cut down ultimate base level. But we also, in Missouri, we have Bagnell Dam, which formed Lake of the Ozark. And so as the rivers are flowing into Lake of the Ozarks, it doesn't know that it's not at sea level. All it cares about is the water has plateaued or stopped. So that would be a local base level for the rivers that are flowing into Lake of the Ozarks. And so when we start looking at rivers, they try to maintain their course. And so if the ground rises up, what's going to happen is you can create either a valley or a canyon. And so a valley has a V shape, valley V. A canyon tends to be more straight down. If we had a crack or a joint, that's going to provide a weak spot. And so as rivers are moving down, they're going to cut further and further down. The other thing that can happen that can cause this area to create a canyon, if we look at the southwest part of the United States where we have a lot of canyons, the entire ground can be pushed up in the Colorado Plateau, and the river is going to want to maintain its course. And so we have these slot canyons where this ground is risen up, and these are occurring when we have some softer sediment beneath some harder sediment, and as a result, it's creating these little nick points, and it's creating some of this undercutting. If we have valley shapes, V-shaped valleys, what can happen, the reason why we have V-shaped valleys is as this river is moving down, the sediment around here will mass waste or slump, in this case, into this river. And so if we get above that angle of repose, it's going to just wash into the river. And so the river is constantly moving materials downstream. And so if we look at something like the combination of hard and soft materials, you can end up with these stair-step canyons. The Grand Canyon would be a really good example of this, where we end up with some softer sediments in brown, and the gray sediments are more resistant, creating those more straight areas, and the softer sediments creating more of the lower gradient valley walls. Now, you can create rapids or very, very turbulent water flow associated with a very steep gradient, and that would be, rapids would be an example of something on the left here. Then you can also create waterfalls where the gradient becomes so steep that the water free falls above the straight bed. And probably the best example of a waterfall here in the United States, or on the edge of the United States, is the Niagara Falls. Now, as the glaciers scoured out a region and then have since retreated, what has happened is it left what's called an escarpment. It's a very long region of the steep gradient. And as the river is now passing over this escarpment, what's going to be happening is the water is going to free fall down. And as this water is moving down, it's going to start to undercut some of these softer materials. And as it starts to wear out these softer materials, it's going to cause the harder materials above to eventually get undercut and then wash off. And so the Niagara Fall is not stationary. It was receding at about 5 feet per year, and now it's going about 3 feet per year. So as this water was falling down 176 feet. Now, if we start looking at the Niagara River, it actually breaks apart, and there's 3 different of these falls where this water is eroding back. And so this undercutting is really playing a role in that. Now, when we start looking at rivers near the mouth, the other end of the stream, those are where we have very, very low gradients. And so these are going to be very prone to flooding. And again, finding the path of least resistance is what rivers excel at. And so if rivers are constantly depositing materials and it starts to fill in one area, the river will just change course and go and find a different location. And so rivers have no problem breaking apart and coming back together to create what's called a braided stream. Kind of looks like braided hair. Now, when we have a low gradient and rivers have no problem changing courses, what can happen is rivers can create something called meanders, side to snake-like view as this river is moving from side to side. And this happens when we start looking at rivers that are not moving perfectly straight. There's going to be one side that might have a little bit more erosion taking place. We call this period the side that is eroding away, the cut bank. And so this water is moving a little faster over here, so the competence of the river is going to pick up more materials. The other side, where the erosion is not occurring, it's going to start to deposit material. So then we'd end up with these point bars and cut banks. Cut banks on the eroded side, point bars at the deposited side. And what's going to happen over time, these cut banks are going to get more and more pronounced and eventually create what's called a meander neck or meander loop as this river is cutting away on the outer part of this loop. And so what can happen here is this area is going to be cut back and this area is going to be cut back, and eventually they're going to meet. And when they meet, what's going to happen is the river is going to find the path of least resistance and leave behind this old meander loop. We call this old meander loop an oxbow lake. So we call this meander loop an oxbow lake, an area that has been cut off. On the Mississippi River, we've got a couple of them. Here's the one from your textbook. Here's just outside of St. Louis. Here's one of the two horseshoe lakes on the Mississippi River. If we go a little bit further south, there's a second horseshoe lake. Makes sense that we would call horseshoe lake. An oxbow is a thing that an ox would wear on its neck, and it looks like this horseshoe shape, where it would help the farmer plow his field. Now, if we have a mountainous region with a very steep gradient entering into a flat area away from the mountain, what's going to happen is the gradient is going to change the competence of the river with therefore change, and you're going to end up with sediments being deposited in this fan shape, like a old-timey fan that you would fan yourself. And so these are called alluvial fans. And some examples of this one is in near Death Valley, where we went from this very steep area to that area that was filled up with a little bit of, looks like a little salt deposits right along in this area, creating that alluvial fan. If we're here in the Gulf of Mexico, the river opens up into a large body of water, in this case, the Gulf of Mexico. So the cross-sectional area got really big. And if we have the same discharge, an increase in cross-sectional area is going to lead to a decrease in the speed of the water. And so that's in turn going to lead to a decrease in the competence of the river. And so it's going to deposit materials. And so it's going to, again, find the path of least resistance and be deposited in this delta shape. The name delta actually comes from the triangle shape that is typically formed as a result of this. Probably the best example of this on the planet is the Nile River, which is a north-flowing river in Africa, which you can really see on a Google Earth image of this triangle-shaped delta. Here's a local example of the Mississippi River. And so when we started looking at the competence of the river, of the Mississippi River, 550 million tons of sediment are carried to the Gulf of Mexico each year. 550 million tons. So that's 1,100,000,000,000, hundreds, millions, billions, trillion. 1 quintillion, 100 trillion pounds of sediments are deposited each year by the Gulf of Mexico. So that means that all that material from the upper regions is being brought down. And so as this river is going back, as this river is meandering, back and forth and back and forth and always carrying materials, with the exception of a flooding event, it's going to be eroding this material. And so when we start looking at these floodplains, uh, while yes, the sediments around the floodplains are deposited, uh, during non-flooding events, the river is constantly washing this material away. And so it will actually create a big, broad, flat area that's being carved out of this region. And so this is going to be the bluffs of these areas. And so this big, broad, flat area is the floodplain. And so you can clearly see where this floodplain was here in Illinois. And we have, oh, look at that dendritic pattern on the bluffs. But this area dominated by this area dominated by farming on this floodplain is a real good example of an existing floodplain, which means it's also prone to flooding. So we'll talk more about that here in just a second. And so what we're seeing here is these small tributaries leading into larger rivers, and these rivers meandering back and forth. And so over periods of time, it's very natural to find these large floodplains if erosion is the dominant feature. I've already mentioned this, but if this entire region lifts up, the river is going to try to maintain its course. And so at one time, the southwest part of the United States did have a river valley, a nice, clearly defined river valley with oxbow lakes. And but what happened since then is the Colorado Plateau has risen up. And as the river trying to maintain its course, what's going to happen is it's going to carve down as opposed to lateral erosion. Rivers that are steeper are going to be more effective at eroding and have faster water moving. And so what can happen is something called stream piracy. So on the left here, we have this river, which has a steep gradient over here, but then in the lower portions, it has a lower gradient. This river over on this side is going to have a steeper gradient. So a steeper gradient is going to lead with more erosion. And so eventually what can happen is this river headward erosion can actually start to break through this drainage divide and capture this portion of the drainage divide. And so what we end up doing is now, over time, we no longer have water in this region. The water is all going in this direction here. Now, when we start looking at rivers flooding, flooding is a natural event that can occur from either heavy rain or lack of drainage. And so when we start looking at flooding, river flooding usually gives us a fair amount of warning that we can take days to weeks to develop, as opposed to flash flooding, which is going to be onset with a very high discharge. Rivers are usually, these drainage basins are relatively small, and water is funneled into these steep valleys very quickly to create these flash intense rains and intense flash floods. So whether you're dealing with a flash flood or river flooding, there are some things that we can look at to engineer to handle these. One of the things that you could do is if you're in an area that is prone to flooding, is during heavy rainfall, don't be in the low-lying regions. And so if there is a flash flood warning, do not go in that region so you don't have to be rescued, like the image there. If you're on a river, and so there's a couple of different things that we can do. One of the things that we can do to have hard structured flood control is to put up an artificial levee. So an artificial levee, what it's going to do is it's going to increase the depth of the river. Remember, the calculation for discharge is depth times the width times the speed. And so in this case, we are creating an increase in height or depth so we can accommodate the excess amount of water. And so it's not uncommon to put up these artificial levees with a flood wall. here's the image from Cape of the flood wall downtown. And so that's one thing that you could do, is to put up these artificial these flood walls to protect certain areas. You have downtown St. Louis is another example that has these flood walls. So to protect the backside of the floodplain and keep the water in one location. The other thing that you can do is restoration of wetlands, areas that are very prone to flooding. Make sure we don't build on those regions, and that does a couple of different things. It allows the water, it gives a place the water to go. We can put up a city park. So this area that is very prone to flooding is going to take in some of those extra sediments during the flooding event, and keep the water from going too high in other locations. Now, we historically would put up an artificial levee to keep the water from coming out of your property. And so if you had a nice artificial levee, you would also have to build one on either side of your property, or rely on your neighbor's levee. And so this was a bit of a problem. In the 1930s, part of the work program was to have laborers go and put up these artificial levees, and put up an artificial levee along the entire major riverway. And this way, the entire structure was built, and it was built to a little bit higher standard, which meant it didn't flood. The downside of this is when we do have these heavy rains, in some cases, we can actually choose where the levee breach is going to occur. And so in 1993, we almost had this problem here, where the hydrostatic pressure of this water over here actually carved underneath and started bubbling up underneath this region. We fortunately were able to protect some part North St. Louis with this, and so the water ultimately, unfortunately for Southern Illinois, the levee breached over in this region. Now, in about 10 years ago now, we had another example of a levee breach. We knew the city of we had a lot of water flowing down the Mississippi River and the Ohio River, and we modeled how high the water was going to get, and it was going to get and inundate the city of Cairo. And so as a result, we did not want to flood this region, so we blew out a part of this artificial levee called the Burge Point Levee, and all of this water flooded into this region. And so again, you can see that there's an old oxbow lake. This is an area that is very prone to flooding under natural settings. And so unfortunately for all this farmland here, the Mississippi, when the Army Corps of Engineers blew this area out, it flooded out this region. So when we start looking at flooding, flood insurance is not part of the standard homeowners insurance. It's a separate policy. And so whenever we're starting to look at floods, we'd like to evaluate risks. And part of this class, hopefully you've realized, is to deal with what are the things that can affect us, and in particular, what's our risk of different events. We've already talked about earthquakes, and now we're talking about flooding, and we've talked about mass wasting. And so we can start looking at probability of risk. And so we can look at rainfall events in the past and how high rivers have gotten in the past. And so what we've collected this data to do is to form our probability risk. And so you may have heard that the 1993 flood of Mississippi was the 500-year flood. And it was called the 500-year flood, not because it happens every 500 years. It's the odds of it occurring were 1 in 500. And so your book talks about the odds of a 100-year flood are not every 100 years, but it's a 1 in 100 chance, or a 1% chance of flooding. And so we can actually calculate this risk. And if you're in the lab section, you will be doing the same flood analysis of looking at this data and creating a graph like this, plotting the data of the reoccurrence interval versus the discharge. And you can see that there's a distinct pattern here of this reoccurrence interval. And so then we can predict what the odds of something, say, the 200-year flood, even though we don't have 200 years of data, if we plotted enough of these points, we can extend this graph out to figure out something. Well, if the discharge of the odds of a 200-year flood occurring, be 0.5% in any given year, and it would have a discharge in this graph of 700. And so we could start to say, if we had a discharge of 700, how high would the water have to be? Oh, it's going to be 10 feet above the banks. 10 feet above the banks would tell us that that a house would be at a higher risk. And so we could actually know your flood zones. We can actually go and collect this data. So the average number of years between successive floods does not mean, or the odds of it occurring between any given year, is the recurrence interval. And so when we start looking at the recurrence interval of, in this case, the 10-year flood, if I drew my line straight up, so I'm trying to use a mouse here, the recurrence interval of a 10-year flood would be about 450 cubic feet per second based on this river using this year, or using this data. Again, every river is going to have its own flood graph like this, and so you'd have to do one for each one of these rivers. Fortunately, as we learned earlier in this lecture, there's a bunch of data that we've been collecting on this. Now, the next part of this chapter is going to be talking about water in the ground, otherwise known as groundwater. And so this only occurs in the upper part of the crust. Eventually, what's going to happen is if we go deep enough into the earth, the rock pressure is actually going to fuse together and seal up any of these cracks. And so when we start looking at these cracks, the total volume of crack, or the percentage of pore spaces, is called the porosity. And so we can actually look at how much of this grain, in this case, how much of this image here is blue, what percentage of it is blue, and that would be the porosity. As a percentage is porosity. And in this case, I would say, I could do a statistical analysis, but I'm just eyeballing this and saying that's about 15% would be about the amount of pore spaces in here. Now, we can also look at the permeability. This is the ability for water to move from one side to the next. And so this is going to depend on the number of, the amount of space, how straight that space is, and how big those spaces are. Now, you'll recall when we started looking at sedimentary rocks, sand is really big chunks compared to little tiny bits of clay that all look like poker chips. And I think I had my poker chip model of a layer of clay. And so when we start looking at things that are literally going to bear water, that's what the word aquifer means. These are things that are going to have a high porosity and a high permeability. And so when we start looking at these things like sand, would be really, really good at having a lot of pore spaces and having those pore spaces connected, so it would be a good aquifer. We can look at clays. Now, clay does have a high pore volume, high porosity, but those clay particles are not well connected. Those little water would have a hard time traveling from one side of a layer of clay to the other. And so it retards the movement of water. And as a result, we're going to call it an aquitard. Now, as water is in this image, as water is passing down, infiltrating into the ground, some of that water is going to be, the nature of water is going to allow it to have surface tension to stick to the individual little grains. But, and so we call this area the zone of aeration. But eventually some of that water is going to seep into the ground and fill up all the pore spaces. And if it fills up all the pore spaces, we call that groundwater. And so if we were going to be putting a well in, all we'd have to do is dig a hole to that water table. And in this case, I have an unconfined aquifer. Now, if you had an old-timey well, just a hole in the ground, you could dump your bucket in there, it would fill up. Um, but there's some problems with that well. It would, if something went wrong over here, if we had some radioactive waste or something like that, I'm just making, get a different color. Trying to get a different color anyway. So if I had some radioactive waste on the ground here, it could seep into the ground just like the water and potentially go into your well. Um, now, the other thing with this unconfined aquifer, where the top of the water table, top of the aquifer is the water table, if we had a drought, eventually that drought could, in fact, all that water could leave this area and then you'd have a dry well. Let's get rid of all the air. If I put in a new well down in this area that is below the aquitar, we'd seal this back up. Then what's going to happen is this water right here in this confined aquifer would not be subject to local drought. And so this is the difference between a confined aquifer and an unconfined aquifer. If you dumped waste in this material, it's not going to be able to get into that well. Again, that well is a sealed tube. So a sediment with low permeability, water can't get through very easily. So in other words, water would be retarded or moved slower. And so this is known as the aquitard. So when we start looking at water, water in the water table, as rain occurs on all places. So what's going to happen is as water is seeping into the ground, it's going to fill in those pore spaces. And so it tends to look a lot like the landscape, only not as much relief. We call it a subdued reflection of the landscape. It's a common mantra when we start looking at the water table. And so it should look something like the water table, with some exceptions. One of the exceptions that we have is if we had a lens of clay, a little layer of clay here. So if we had rain occurring in this area, the water seeped all the way down to that unconfined aquifer, but in this area, it hits this clay. And so as a result, farmer A could have a very shallow well where farmer B right here would end up with a dry well. They're in that zone of aeration above, they'd end up the dry well. They'd have to go down significantly lower. And so we call this, again, this water table that's perched above the main water table. It's called the perched water table. So groundwater is always moving. It's due to both gravity, the overlying material, but it's also due to hydrostatic pressure. So if we take a look at this point in the water table and this point in the water table, this point A, or point P1, has a lot more water on top of it, so it's got more water pressure. Point 2 has less water pressure, and so this water is actually going to move in that direction to go from the higher pressure to the lower pressure. This is known, we can actually calculate how fast this water is moving, and this is known as Darcy's law. And it's an equation that we can actually monitor the rate at which water is flowing. And so when we start looking at water, we want to know what is the recharge area, what area is getting contributing water flow. Much in the landscape, we have the drainage basin. In the ground, we have a discharge area. So this is the ground area that has groundwater flow from the surface into the ground. And so we can actually plot which way the water is flowing. In some cases, if the water table hits the landscape, water is going to seep right out of the ground, and we call these seeps or springs. And so in this case, the water is hitting the ground, and so we have this water literally washing out of the ground. So we can actually monitor this water flow. And so in this case, if we didn't have this area in the bottom right, the water would flow. This is not a topographic map, but a map of the water table. And so if we have water, the water over here is 414 feet above sea level. The water over here is 400 feet above sea level. So the water would flow from the 414 down to the 400. And so what you're actually creating are these lines of water elevation, and the flow lines would create something called a flow net. And so we can actually plot and track where water is flowing. Now, in this case, on the bottom right-hand side, they put a well in. And so they're lowering the water table in this area. And so they actually are changing the water flow where the water I want to kind of point out this arrow right here, the water would have been flowing into the river in this case, but by putting this well in, we were actually drawing water from the ground into this well and changing the direction of this water. Now, most of you are getting water from groundwater one way or another. You may say, wait a second, I'm getting my water from the tap, from a faucet. Yes, but a lot of times around here, the water is coming from the ground, because as water is moving through the ground, you have ion exchange and this natural filter occurring. And so it's a very, very effective way at keeping water much cleaner than surface water. Surface water, you have to worry about pathogens and all sorts of anything on the landscape that can wash into those rivers. Now, in some around here, in places like Fredericktown and Ironton, and well, basically most of the Arcadia Valley, if we look at the rocks around there, we have igneous rocks. Igneous rocks don't have many pores, so you have a porosity nearly zero, maybe a couple of cracks where the water would flow, but definitely not enough to have an entire town. And so what we need to do in those locations is dam up a river and have a lake, say City Lake, that you can actually obtain some of this water from. So when we start looking at water that flows out of the ground naturally, is known as a spring or a seep. Now, I've already kind of started talking about wells, but an ordinary well is just a hole in the ground, and more times than not, your map, your textbook has the pump above the ground. Usually, the pump is down here. It's easier to push water than it is to pull water, and so either case, you're taking water out of the ground, you're lowering the water table, and you don't want to potentially have this water moving very quickly and pull in some sediment. So they will usually line this with a screen and then put some sand in there and put a little pack in there, sand pack in there, to allow that water to pass through and act as a filter. But if you're pumping more water than is falling as rain, what's going to happen is you're going to lower the water table in two directions. In two dimensions, it looks like a V, but in three dimensions, it would look like a cone. We call this a cone of depression. And so this cone of depression, in this example, we have two wells with two different cones of depression. Note the well on the right is a larger well, so it's taking more water out, and so the cone of depression is larger. And so in this image over time, what happened is this cone of depression actually diverted the water and lowered the water table so much that the cone of depression's impact, is actually causing this secondary well, this shallower well, to go dry. And this is a common occurrence in places that are relatively more arid. And so you can end up with some very, very, very inhospitable neighbors if you are, in fact, causing your neighbor to go dry. We have something called artesian wells. Now, artesian wells are wells that have water that will rise up in the well tube without an actual pump. So how can you get water to flow out without a pump? We can use that hydrostatic pressure. So if we look at this area on the left here, this area has higher pressure. And so as a result, this water the water on the left side is going to push down, and it's actually going to push this water out. And so we have a naturally flowing well. I know over just south of Fredericktown and Marquand, we have one of these natural flowing wells. Now, I didn't grow up around here. I grew up in the Chicago region, but we had a natural artesian well in a city park, and it was great. It was nice cold water. And they did a little tracing of that water and they actually tested that water. And then in the 1990s, they said, don't drink that water. Um, Now, normally artesian wells tend to be thought of as cleaner wells because if you had some, say, toxic waste over here, well, this ordinary well would be affected by that. This artesian well would be um, protected because the contaminant wouldn't be able to get through the aquitard. Unfortunately, as this water was passing through these shales, it was picking up bits of radon gas in my hometown. And so as a result, the water that was coming out had too much radon in it, substantially too much radon. And so they stopped allowing people or put signs up that said, don't drink this water. So just because it's artesian wells does not necessarily make it cleaner. And so if you live in places like Farmington, Bonne Terre, Park Hills, you're getting wells that are coming from this unconfined aquifer here, unconfined aquifer. If we're in Park Hills proper, 10 years ago, we know there's a big cavities in the ground here in the mines, and they were pumping some of the water out of the mines. It's still that groundwater, and so it was readily available. In fact, in Bonne Terre, if the water table gets too high that it impacts the billion-gallon lake in the old mine, they will actually pump the water out and dump it into Big River further downstream. So this way, they can lower the water table enough that they can go and have tourists going to go do some scuba diving. Another natural occurrence with groundwater is hot springs. Now, you have to be near a magma source for a hot spring to exist. And so what's going to happen is water is seeping into the ground, comes in contact with this hot water, and then the water is returned to the surface to create these hot springs. Geysers can occur in a similar way. Remember, water is under pressure in this case, and water under pressure won't boil at 100 degrees Celsius. It could be significantly hotter depending on the amount of water pressure. And so what's going to happen is this water can become superheated. And if this water around here is superheated and then starts to rise up, immediately when it's under lack of pressure, it's going to turn into a gas. And when it turns into a gas, it's not going to take up as much space. It's going to take up more space, excuse me. It's going to really expand, and it's going to push the water above it up. And so this is why geysers exist. One other common occurrence that's associated with groundwater, particularly here in places like Missouri that have a high amount of limestone, is these things called caves. Now, caves are just cavities in the ground. We learned in chapter on minerals, I think it's chapter 3, that calcite is easily dissolved with an acid. And so if you had a rock that was made with acid and we add some organic material in the soil, which are going to produce some carbonic acid. Acidic carbon dioxide plus water is carbonic acid. And so if you have this carbonic acid hitting this limestone, you can start to dissolve that limestone to create these caves. And so these caves can follow joints. In other cases, the caves can find whatever path. Maybe we had a joint set associated with some rock under stress. And so what's going to happen in the zone of saturation where you're underwater is you can dissolve these large cavities. These large cavities eventually are going to find, this water is going to find a place to go out, usually along a river. And as a result, that water is going to be drained. And so if it is drained, then we have a cavity in the ground. If we have an entrance point, we call it a cave. And these form, again, just below the water surface in that zone of saturation. And then after the cave is formed, we have this cavity, water is still flowing through there, but now the water has a place to go. And so as the water is going into this cave, the water can evaporate, leaving behind its dissolved mineral, usually limestone, to create these speleothems, a fancy name for saying cave formations. And so calcite is usually produced forming in the mineral called a rock called travertine. And as the water is evaporating, it creates little icicles hanging tight to the ceiling, C for ceiling, called stalactite. And then if they are on the ground, they might grow up. They're called stalagmites, and eventually they can form together to form a column. And so we can form these huge cavities here. So stalactite near the ceiling. And so we have a lot of these different types of stalactites and stalagmites, and some very unusual features here in Missouri. One of which unusual feature associated with cavity, limestone and karst topography are these things called sinkholes. And this is simply when the cave gets so large that the overlying material cannot withstand this material, and it will start to sink. And so as a result, creates this sinkhole. And sinkholes are typically going to be this rounded shape, and they're going to fall down all the way to the water table. And you can see in this map of Missouri, we have lots of these sinkholes locally as well as across the state. And if you look at a superimposed map of Missouri's geology, we'd see that these are all associated with this limestone or dolstone, which is limestone with magnesium. So we call these areas karst topography or karst landscapes, where these sinkholes are produced. It's very common to have rivers that are flowing around on the landscape and then go into the sinkhole, and then the water disappears. We call these sinking streams or disappearing streams. So that's not uncommon. And so we can also end up with these tower karsts, a region created by erosion of the ridges between sinkholes, like the image on the right there. So again, karst topography is associated with groundwater being dissolving these large cavities. And so this river, you'll notice, is getting lower. So it's lowering the water table in this region as it's dissolving these rocks. And so you're going to end up with lots of these sinkholes. And it's in some of these cases, these sinkholes will have water in them because that is in fact a window to the water table. Now, when we start looking at some of the problems associated with, or potential problems for fresh water, since we use fresh water for a lot of, obviously for drinking and human consumption, unfortunately, we can have water pollution activities where adding pollutants to waters to make them unsafe to drink. There's been a number of different types of pollutants when you start looking at water. Some of these pollutants will float above the water. These are called LNAPLs. These are where things like oils, which will float on the water. And so that means that they're going to seep into the ground, hit the water table, and move along the top of the water table. We have some other pollution which will be more dense than water. And so it will sink to the bottom of the aquifer. And so knowing what the pollutant is can help us deal with that pollutant a little bit easier. And then obviously some pollutants can be dissolved in the water itself and move just like the water. We can track that water with those flow nets, so we can actually figure out where the water is coming from and where is the water going to go. So when we start looking at groundwater, pollution is a big issue. And anything that happens in that drainage basin, eventually, whether it's going to be through runoff, whether it be through seeping into the ground, is going to have its impact on that basin, the water in that basin. One other problem associated with with water in general is eutrophication, abundant lifefication. Abundant trophification, a process of having an abundant amount of life. Now you may say, what's wrong with having an abundant amount of life in the river or in a lake? Well, this life is usually algae, can grow really quickly, and then you can end up with algae eaters. And the algae eaters are going to also reproduce really quickly and use up all the oxygen. And so what happens when you use up all the oxygen, other organisms that rely on this oxygen will have to die, would die off and create areas that, again, dead zones are common of reference if you want to see where some of these eutrophication occurrences occur. So if you have a farm in this area and you end up with more nutrients washing into your river or into your pond, you can end up with having a fish die off. One way to solve this would be to add extra oxygen back into the water. And so a fountain, turbulence is a great way of adding oxygen into the water. Oxygen, the atmosphere is about 20% oxygen. So if you mix this water around with the atmosphere, you can get more oxygen into the water. And so we naturally do this with rivers and turbulence, but if you have something like a lake, again, you can do this with a fountain. Obviously, dam construction has a big impact on the flow of water. You can end up with damming up the river is going to change the water table. It can also cause water that was shallow and getting a lot of sunlight to become much deeper and cooler. And so if you're blocking the water, you're going to change the competence and the capacity of the river. So there's all kinds of impacts of dam construction on a river. Obviously, the benefit of dam construction allows us to have a hydroelectric power. In the example of the two farmers with their competing wells, they can lower the entire water table. The High Plains or Ogallala Aquifer is a famous example of an area in Kansas and Nebraska and into all the way down to North Texas that has undergone this water depletion. And in addition to that water depletion, the water table can lower so much that the pores, which had water in them, now have air. Air is easy to squeeze, and so the entire region can start to compress and lower the porosity of that soil or rock after the fact. So as I was saying, groundwater depletion, as we looked at in a previous slide, water being removed from this environment can lower the water table, and that would have a real big impact on rivers or dry. It can actually cause swamps to dry. And we start looking at groundwater contamination. Here's some common sources of groundwater contamination. We have acid waste mines. A lot of times we'll use acid to remove sediments or remove minerals out or elements out of certain minerals. And so we can actually use that leftover acid can get into the groundwater. We can also have septic tanks. If you have a private well, you have a place that you're going to have to eventually get rid of your waste. And that's usually a septic tank, which is a hole in the ground. And under natural circumstances, this septic organic material will break down as long as you wait in long enough of a space. The organic material would break down, you'd have those ion exchange. We have things like gas that could potentially leak and gas additives from tanks. In this case, I have a couple of friends that went into groundwater management, and so they made a living dealing with leaky underground storage tanks, or LUSTs. And so those were basically what they would do. They would go and go to gas stations, determine if this pressurize a little portion of this tank and see if the pressure stayed held, or if the pressure drained, meaning that the tank was leaking. And so then they could actually had to go in many cases figure out which way what contaminant was going to be going and how to clean up this contaminant. If we have a flow net, we can figure out which way the water is flowing. We have some surface tanks and salt piles, which again, salt can be get dissolved in water and have problems. And so we have landfills. Again, I've got a friend who did landfills. Typically, what you would end up with a landfill is a layer of an aquitard. You would actually build in an aquitard around the bottom of this clay, around this landfill, and then you'd cap it with another layer of clay, and so you'd entomb that waste with two package. You basically make a giant baggie for that material, and then you would set up a series of pumps and pump any water out from around this landfill. Um, Animal waste can be a problem, as well as excess fertilizers can get into the water. And then one thing that's been in the news in the last couple of years are PFOS, which are sometimes dubbed the forever chemicals, which have a very long, they don't break down very easily, and so they can be a bit of a problem because they're going to stay in that water. So when we start looking at these wastes, let's see, changes in infiltration and supply, sediment supply. If we start looking at this river here, it's carrying sediments downstream, but if we start pumping out all of this water, we could cause this river to go dry, and then no sediments would be moving further down. And again, these sediments are going to eventually, in the low-lying areas, are going to provide the really rich soils to the farmlands. And so a lack of water moving through this area means that the farmlands in the downstream area would be impacted. So if you have any questions, be sure to let me know. Have a great one.